So let me explain the big O rules for polynomial numbers. By the way, these slides are from Dr. Park's Data Structures and Algorithm course. It's just a brief introduction to prepare next advanced course. So you are going to learn in detail about this time complexity analysis though. So these are the general rules. So ignore constant factor if you have time complexity is n or 3n or 4n, even if 1 million n, just ignore constant. It's all big O of n. Ignore lower order terms. So if we have something like this, ignore any lower order term. Keep the highest order only, so big O of n squared. So in general, if fn is a polynomial, means something like this, then only take the highest order and drop constants. Then that's a big O, time complexity. And whenever you find the big O, find the smallest possible function instead of something bigger. So if 2n is there, then the big O of n is the closest, the smallest big O, but n squared is still satisfies that, but smallest possible is a big O n. So the right answer is a big O of n instead of a big O of n squared for time complexity is 2 times n. So then for logarithms, here is some logarithm based computation. So if you are not very familiar with what this formula shows, that then what it basically says, ignore the base of a logarithm. If a log is a base of b or a or n, it doesn't matter, simply ignore that. That's the general rule when you deal with the logarithm time complexity. And if we have a logarithm complexity, it is always smaller than any n to the rth power, like n. So what it means is basically if your time complexity is log n, then log n, then which is worst case or equal to n. So big O of log n is always smaller than big O of a linear function. That's the last bullet says. And then big O rule of exponentials. Then exponential function is always growing faster than any polynomial one. So if you have a 2 to the n or 3 to the n, whatever n is an exponent, then this is always growing faster than any polynomial n to the whatever power, something like that. Even if this is a big number, 100, so polynomial is as the data size becomes bigger and bigger, and then exponent is growing faster. So that's what big O general rule explains here. Now let's get to the how we get those big O time complexity from the given program code. First, if we have a simple loop like I goes 0 through n, and each time I is incremented by 1, and within the for loop, what you do is independent of n, just a fixed operation. When I is provided, simply addition is there. So running time is a number of iteration. So which means big O of n if n is the data size there. In nested loop, we do inner loop we do n times, and the outer loop we do n times for the inner loop. So that is n times n is a total number of operations. So big O of n squared if you have a nested loop. Here the n squared strictly, then each inner or outer loop goes 0 through n, 0 through n strictly, and then incremented only by 1, then it is a big O of n squared. and the consecutive statements. So here we have one statement of a for loop, another statement of a for loop. Then running time is add those two. So first one is 0 through n, I is incremented by 1. In the for loop body, it's a constant time operation. So the first loop is time complexity is order of n, and second one is a nested loop. So we do n squared times. So this is a order of n squared. So if we find the time complexity for the entire program, which is order of n squared plus order of n, then we ignore lower order. So overall, the whole program time complexity is a big O n squared. So if you have a conditional one, if or else, then order of this part, order of that part, whichever is bigger is the time complexity of the entire program. So here is exercise to apply those knowledges we have learned so far. Suppose always in the program n is the data size. Then in this first program, the program is not dependent upon data size n. It's just a fixed one, so it's order of 1, constant time. Second one, we have n here, but we go from 0 to n squared each time I is incremented by 1. So we do operation n squared times. So order of n squared. The quadratic function is the time complexity for exercise 2. Now exercise 3, it's a little bit complex, but I begins 1 and I is less than n. Suppose always in this exercise n is the data size. Then I is not incremented by 1. Its I is doubled every time. So 1, 2, 4, 8, 16, and the like, 32, 64, and the like. That is n. Then how many iterations we do? So if we have a 64 data, for example, then how many operations? 1, 2, 3, 4, 5, 6, 7 times, and the like. Then what is the relationship between this one and then how many times? Then we just compute the log 2, or what is the index of each number if it's a power of 2. Then it's a 0 index 1, this is a 2, this is a 3, 4, 2 to the 5, 2 to the 6, like that. So as we go up to 64 data, how many operations we need to do is about 6 times, 6 plus 1. If we have this many data, we need to do iteration 5 plus 1. And this many data, 4 plus 1. So what's the relationship between this number and the exponent? That's a log n relationship. So question 3, it's a big O of log n. And this one, I goes 1 through n each time by 1. J goes 1 through I each time by 1. So it's approximately n times n. Actually, it's not n times n though. So we do n first n times n times times n time n plus 1 and n plus 2 and so on. But overall, it's a worst case is n times n. So quadratic function is time complexity. Number 5 begins with n. Each time I becomes half of that. So that is a reverse of 3. 3 is begins with the 1 and then go to n by doubling that, and then beginning with the big maximum number goes down by half. So it's exactly the same relationship, but operation is going backwards. So how many times of the iteration we do? Log n times we do. So that's a logarithmic time complexity. We find that. And then number 6, I goes 1 through n. Always remember n is the number of data. In the loop, what you do is j goes I to 100 fixed. So inner loop is independent of n. Independent of n. So which means a constant time, fixed time. So the overall, how many iterations is a big O over n. It's a linear complexity. Next, I from 1 to n squared each time I is incremented by 1. So outer loop goes n squared times. Inner loop begins with 1 to I. I is represented by n squared, worst case. So inner loop is also n squared times. So overall, its time complexity is n squared times n squared. Then the fourth power, that's approximate time complexity analysis.